Hi everybody, Physics Ninja. Today I want to look at the Carnot Cycle. So what we're going to first do is just review what the Carnot Cycle looks like on a PV diagram. I'll describe all these processes, the isothermal, the adiabatic processes, and what are the equations that we can use to calculate, for example, pressure, volume. What if I was interested in calculating the work, the heat, or the change in internal energy of a gas as it goes through this cyclic process? Okay, at the end, my goal is going to be to fill out two tables. Okay, the first table shown here up above has all pressure, volume, and temperature data for all of the key points on the Carnot cycle. And table 2 will involve calculating the heat, the work done on the gas, and the change in internal energy of the gas as it goes through the different stages of the Carnot cycle. Alright, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support Physics Ninja. Alright, let's get started. Alright, so here's the problem. We have 2.34 moles of a monoatomic gas, okay, which has a pressure at point A here of 1400 kilopascals and a volume of 10 liters. Now, if it is a Carnot cycle, I am going to go from point A to point B. First of all, this is an expansion, right? Because the volume is getting bigger as I go that way, right? So that's very important. Okay, and this first process is something called an isothermal process. That means every point along this line here, there is no change in temperature, which is why I wrote here delta T equals to 0 everywhere along that black line. The next step of the Carnot cycle is going from point B to point C. This is also an expansion, right? Because the volume is getting bigger. Okay, I'm also telling you that at point C, this volume is 24 liters. All right, now this process, this blue line here, is called an adiabatic process. And what that means is there is no heat exchange between the gas and the environment, okay? So there's no heat going in or leaving, okay? So it's kind of a nice isolated system. Now we're going to start going back the other way. This orange line is represented by another isothermal process. So again, the same rule applies, right? There is no change in temperature everywhere along that orange line. And the last one here is also an adiabatic process. The volume is getting smaller as I go toward point A. And again, there is no heat exchange during that whole green line process. All right, so now we have to go and apply a couple rules and review ideal gas law and some rules concerning adiabatic processes in order to fill out my first table. So let's go ahead and set that up. All right, so here's table 1. I have pressure in kilopascals, volume in liters, and temperature in Kelvin. I've listed some of the values that I've given you in the problem here. So at point A, I know the pressure and I know the volume. Now, these are not standard units. Usually you have pressure in Pascal and volume in meters cubed, but we'll just leave it like this for now and I'll show you what happens. I've given you the volume at two other points on this diagram. Okay, at point C, there is a volume of 24 liters. And at point D, there's a volume of 15 liters. Now, the key to filling out this table here, we're going to have to use some relationships, but one equation that we can use is the ideal gas law, right? Our ideal gas law says that anywhere in this diagram, pressure times volume must be equal to nRT. Okay, so if you know two variables, you automatically know the third using the ideal gas law because I've given you the number of moles here. So let's go ahead now. That means we should be able to calculate what is the temperature over here at point A. All I would do for that is, so at point A, I would say, well, the temperature at point A, let's rearrange this equation here and isolate temperature, is the pressure at point A multiplied by the volume at point A divided by nR. All right, so what do I do now for this pressure? Well, you just take the value. So it's 1400. Now this is kilopascals. Well, I really want that in pascals, right, if I'm working in standard units. So I really want to cancel out kilopascals and I want pascals. And I know in 1 kilopascal there is 1,000 pascals. What else for the volume? I have a volume of 10 liters. Now I want to get rid of liters and I want to get meters cubed. The conversion is that in 1 meter cube, I have a factor of 1,000. I have 1,000 liters. So one thing you notice right away is that both of these 1,000 factors that you end up putting in end up canceling out. So this works. If you just multiply both of these values, you're going to get the right units for temperature. So I'm not going to worry about those for the rest of the problem. All right, now we are left with the number of moles, 2.34 moles, and then the ideal gas constant is 8.314, just the number. All right, I put the numbers in the calculator, and I get something that is around 720 Kelvin. So let's go ahead and put that in our table. 720 was our calculation here. So that's good. So we know the temperature at point A. Now, how do we figure out all these other values over here? So let's go on the next page and think about how we can approach this now. All right, before filling out the rest of the table, let's go back and consider some of these processes. Now, I want to link some of these variables together, the pressure at A, B, C, and D, for example, or the volumes and the temperature. So isothermal means we have constant temperature, right? So let's write that down. T is a constant. Now, if you think about our ideal gas law, if this variable is a constant, right, along, say, anywhere along this black curve, right, we have isothermal process, or along this orange curve. It's a different temperature, right, from the black, from the orange, but everywhere along that orange curve, it's still a constant temperature. So that means, for example, let's consider the point going from A to B. That means this whole right side of the equation would be a constant. I'm not changing the number of moles. I'm not changing the gas constant. And now I've told you it's isothermal, so the temperature is the same everywhere. So that means that the temperature at point A must also be equal to the temperature at point B. That's what it means that the temperature is constant. Okay, that means it's 720 everywhere here along here. So I automatically know that the temperature here has to be 720 because it's isothermal. Now, it also allows us to write a relationship for pressure and volume then, because if this whole right side is a constant, it means that the pressure at point A multiplied by the volume at point A must be equal to the pressure at point B multiplied by the volume at point B. This is a very important expression. Let's call it equation 1. Now, if I use the other isothermal process, again, the temperature is different than the first one, but I can still write this important relationship that the pressure at point C multiplied by the volume at point C has to be equal to the pressure at point D multiplied by the volume at point D. These are two really important relationships, and they're going to help us fill out the rest of the table. All right, for adiabatic processes going from B to C or D to A, the relationship is a little bit different. All right, instead of being the product of pressure times volume that is a constant, it ends up being something that looks like this. It's the pressure multiplied by the volume raised to a power gamma, okay? And this value is a constant number for everywhere along the blue line and along the green line. Now, the gamma factor for a monoatomic gas is a constant. It's 5/3, so very easy to apply. So now we simply write down this expression. We can link now points B and C because this is an adiabatic process. So that means if I apply my new relationship here, I'm going to get the pressure at point B multiplied by the volume at point B raised to that power has to be equal to the pressure at point C multiplied by the volume at point C raised to the factor gamma. Okay, that's equation 3. And similarly now for this other adiabatic process, that means you have the pressure at point D, volume at point D to the gamma equals pressure at point A, volume at point A raised to the gamma. Okay, these are going to be 4 expressions that I'm going to use to fill out this table along with this ideal gas law. Now, this first expression that I wrote for adiabatic processes, it is possible to write down other expressions. Let me show you. Instead of only linking pressure and volume, I could have an adiabatic equation here that involves pressure and temperature, for example. And let me show you how you would do that one. So, well, or I'd just write the pressure, and instead of writing volume, let me use the ideal gas law and eliminate volume. Right? That means you would have nRT divided by pressure, and I have to raise that to the gamma, and that was equal to some constant value. Now, if you distribute this exponent, this expression ends up looking like this. It's 1 minus gamma for the pressure. I get temperature that's raised to the gamma now, and now I'm going to have the number of moles and the ideal gas constant. That's also raised to the gamma, but that's just another constant. If I bring that to the other side, I simply have just another constant, call it constant star. And now I have another relationship for adiabatic processes, but this one here doesn't involve the volume. I could do something similar and eliminate the pressure, again, using the ideal gas law, and you could test this out for yourself, but it looks something like this. You get temperature multiplied by volume to the gamma minus 1, and this is going to be equal to some other constant again. Anyway, there's 3 relationships you can write for adiabatic processes in order to help you fill out this table. All right, let's go to the next page and work on the table a bit. All right, so to start filling out the table, what I'm going to do here is I'm going to look at, for example, going from D to A. I know everything at point A here, so let me use some of that information. And I also know the volume at point D. So guess what? If I use this expression over here, I know volume at point D, I know pressure at A, volume at A, I know the gamma. I could basically find what the pressure at point D is, right? So let's think about this process here. This is the adiabatic process. I use expression 4. I can write that PD is PA. And now I'll just group these terms together. This is VA over VD raised to that power gamma. And now I just substitute, right? So the pressure at point D should be equal to 1400. I can leave this in kilopascals. That's fine. It's going to give me my pressure at point D in kilopascals. VA was 10 and this is 15. I've given you that number in the table, and this is 5/3. Put that in the calculator. You should get something that is approximately 712 kilopascals. So now I can go ahead and put that in this figure. So we have 712 here. Now, if you know pressure and volume, you simply use ideal gas law, for example, and I can calculate what the pressure is now at point D. So the pressure at point D is pressure at point D, volume at point D divided by NR. Put my values in here, 712. Volume was 15, 2.34, and 8.314. All right, my temperature that I calculate with this is approximately 549 Kelvin. All right, and put that in the table, 549. Well, guess what? If I know the temperature at point D, now you can kind of go backwards here, right? That means everywhere along this orange line, since it's an isothermal process, the temperature is the same. So you automatically know the temperature here, 549. Right? So there's really only 2 temperatures for this entire Carnot cycle. All right, now let's think about how can you get the pressure at point C? You know the volume and the temperature. You can go back now and calculate the pressure at point C. Let's keep going. All right, so for point C now we're interested in the pressure, but I know the volume and the temperature at point C, so therefore ideal gas law is kind of pretty simple to use. Simply write the pressure at point C, nRTC divided by VC, substitute our values, 2.34, 8.314, temperature we just calculated was 549. All of this over 24, that was given in the problem. Put that in a calculator, I get that the pressure at point C is approximately 445. Again, we're dealing in kilopascals here, so 445. All right, now we still have 2 values. I need to know what the pressure and the volume are at this point. For this now, we're going to use another one of our relationships. So let's go to the next page and I'll try to show you how to do that. Again, I want to focus on here. I know the temperature here. If I'm looking for the volume, maybe it's easier to use one of the other adiabatic expressions to try to link those together. Okay, let me show you how to do that. So to solve for example, VB, I'm going to use the other adiabatic expression that links the temperature and the volume together, right? Because I know temperature at these 2 different points, and I also know the volume at point C. So I can easily calculate the volume at point B over here. So now let's look at that expression over here. So we have that the volume at point B raised to the gamma minus 1. Let's just leave that factor there for now. It's this ratio of the temperatures, right? These are just values that I know, and the volume gamma minus 1. All right, now to eliminate this, well, think about what gamma is. It's 5/3, right? So you have VB, 5/3 minus, say 3/3 minus 1 is 2/3. Okay, so now it's temperature, oops, not V, temperature rather. TC, TB, and again, VC to the 2/3, right? Because of that subtraction here. Now you simply raise both sides to the power of 3/2, right? And you're going to have VB by itself. So you have this ratio of temperatures to the 3/2. And now if I raise this to the 3/2, this simply becomes VC. So now I just substitute my values in here. So the temperature I had 549, I have 720. This is to the 3/2. And the volume at point C was 24 liters. I substitute that value and I get approximately 16 liters. All right, so I can go ahead and put that in the table. Now the last thing you're left with now is the pressure at point B. Just use ideal gas law again. So you have nRTB over VB. We substitute in all our values here for the temperature at point B, the volume at point B. Go ahead and write that out. You get around 875 kilopascals. All right, so I filled out the entire table now, so I know the pressure, the volume, and the temperature for these 4 points that are important for this Carnot cycle. My goal now is to go back now and use this data in order to calculate 3 quantities. I'm interested in is what is the work done by the gas, okay, along each one of these processes. What else? I want to know if there's heat going into the system or out of the system. And I'm also interested in the change in internal energy of the gas as I go around. So let's go do that now for these 4 different steps of the Carnot cycle. All right, we've done quite a bit of work to fill out the table 1 now. For table 2, table 2 involves 3 different quantities, okay? It's the heat either going into the system or out of the system. So we'll have to define that. We're going to calculate the work for all of these different processes. So notice that sometimes you have an expansion, sometimes a contraction. We also have isothermal versus adiabatic processes. So how do you calculate the work? And also the change in internal energy. Now these 3 variables are linked using the first law. So we're actually going to start with just reviewing that, and then we're going to work at filling out this table. So let's see how each of these quantities here are calculated, okay, for different types of processes. And let's review the first law that links these 3 variables and make sure we're all on the same page. All right, we first want to look at how do you calculate the work. Again, we know that the work done on the gas is equal to minus the work done by the gas. So whenever you have a PV diagram, it doesn't matter what the shape of the curve is. It could be rectangular, it could be curved like this, like isothermal or adiabatic curves. The work is simply represented by the area under the curve, okay? So you simply, if you have a curve, you have to integrate this function to find the area under the curve. If it's a simpler shape, maybe you could just use some basic geometry to calculate the area. Now, the only thing we're worried about now is we want to know what is the sign of the work. So we either have an expansion where the volume is getting bigger, or we have a compression of the gas. And this just tells me the direction of those arrows. Which direction is the process going? Now, it's easier to look at the work from the sign of the work done by the gas, because the gas is inside the cylinder here, and it's providing a force against that piston, right? So imagine this case here of an expansion, right? That means that the gas is pushing against the piston, and I'm going to move the piston a certain distance delta x. If you remember from mechanics, whenever you had a force and a delta x in the same direction, that would mean that the work done by that force would be positive. So this here is represented by the work done by the gas during expansion has to be positive work. But I use my expression up here that tells me then that the work done on the gas, that is by the environment, has to be the opposite sign of that. And the reason that this is important, this is the way that I use the first law of thermodynamics. All right, now it has to be the exact opposite now for the compression. Again, you consider a compression where there's a gas that is producing a force against this piston, but in a compression, the displacement is opposite, right? So whenever you have a force and a displacement in opposite direction, it means that the work done by that force has to be a negative value. So in this case here, the work done by the gas has to be less than 0, and the work done on the gas by the environment, again, that's producing a force from the outside that's pushing to the left, and the displacement is to the left. In this case, this here is going to have to be positive work. So now let's go for our isothermal process and the adiabatic process and see how we calculate the work for both of these cases, because now we have to integrate this area. All right, let's first consider the process A to B, that isothermal process. The temperature everywhere on that black line was 720, and now I'm interested in calculating the work. The work is represented here by this area under the curve, right? That was the work. Now, is the work going to be positive or negative? Again, we have an expansion, so the work done on the gas, again, by the system here is going to have to be less than 0. Okay, the way we calculate the area under the curve, again, you have to integrate, right? So the area would be represented by, I'm going to put a negative sign in the front, okay, to remind me that it has to be less than 0. And this is integration of this pressure over the volume. And I'm integrating now from my initial volume of VA all the way to VB for this case. Now, the way that you integrate this function here is to get rid of pressure, you have to simply use the ideal gas law, right? So you have nRT, right, divided by V, then you have dV. Now keep in mind that everything here in the numerator is a constant for this process because it's isothermal, right? So you can take it out of the expression. So the work done on the gas then is minus nRT, and I'm left with this integral from my initial point to my final point of dV over V. Now this integral is the natural log, okay? So you substitute that and you get the natural log of my final over the initial. That represents this whole blue area here. And the negative sign is just to make sure that I have the proper work for an expansion. So now we could substitute all our values in here because we know the volume everywhere, right? We calculated that in the first place. So let's go ahead and do that now. The volume at point B was 16, right? And the volume at point A we know was 10. So all you do now is you substitute in our values, right? The picture is clearly not to scale here, but that's okay. So we have minus 2.34 for the number of moles, 8.314. The temperature was 720 for this process, and then the natural log of 16 over 10. Again, put that in the calculator, you get minus roughly, just keeping 3 significant figures here, 6580 joules. Okay, that's the area represented by that blue case. Now we have another isothermal process, so we can actually use the same expression. We just simply have to choose different volumes, but let me go ahead and show you where that other isothermal process is. Again, is going from C all the way to D, right? So in this case, you're looking for this area right here. Again, it's kind of the same approach here, except all we have to do is change the variables B and A, and we have to change those from C to D. Okay, so in that case here, the work done, let's just go from C to D. The temperature for that isothermal process, this guy right here, all along there was 549 is what we had. So the work done on the gas for that case, again, it's minus nRT, natural log. Now just make sure you have this right. My final here would be the volume at point D, and my initial here would be the volume at point C. Now we can go ahead and substitute the values here. So again, we have minus 2.34 multiplied by 8.314. Temperature is 549. And now we had natural log of our volumes. And the volume here at D is 15. That was given in the table. And also the volume at C, I gave you that was 24. All right, I put that in the calculator. So the volume on the gas. Now notice this fraction here is less than 1. Natural log will give me a negative, and that's going to take care of this here. So at the end, for this process here, the work done on the gas by the environment has to be a positive value. And this is what we get, okay, 5,020 joules. So we can start filling out our table now for at least the work for these isothermal processes. All right, I put the two numbers here in the table. Now I'm also going to look at the change in internal energy, and I've written a formula here. This is a definition, okay? The change in internal energy is equal to little n, the number of moles. This quantity CV is the heat capacity, and for a monoatomic gas here, the value is 3/2 multiplied by that ideal gas constant. So when you stick everything in, you get into this highlighted equation here. Now, One thing to notice is it depends on the change in temperature. However, we do have two processes here, right? Processes A and B and C to D are isothermal. That means there is no change in temperature for both of these. So there can't be a change in internal energy for both of those cases. All right, now if you think about our first law of thermodynamics here, which I put the equation over here, since you know two of these quantities, I should be able to calculate Q, right, for the isothermal processes. This should be straightforward. Delta U is 0 for both of those. So you see that for processes A and B and C to D, you have to have that Q is minus the work on the gas. So that means for this case here, I'd have 6580, positive 6580. And for this case here, I'd have minus 5020. Okay, so that's it. That's how you can calculate those quantities. Now let's go on the next page and consider what's going on here with the adiabatic processes, B to C and D to A. All right, processes B to C. We want to calculate all our quantities. The first thing that we notice is it is an adiabatic process. The definition of adiabatic, it means that there is no heat exchanged going into the system or out of the system. So whenever you have an adiabatic process like this, you simply go to your table and you put 0 here for the heat. So that means, if you look at the first law of thermodynamics for both of those processes, it means the change in internal energy has to be the work done on the gas, right? Because Q is going to be 0 for those cases. Now, we can easily calculate the change in internal energy. So let's do it for B to C, all right? Our change of internal energy is going to be 3/2 NR. Now, what is my delta T? It's T final minus T initial. In this case, the T final is C, right? So it's TC minus TB. Now notice this guy over here is going to be a negative number, okay? Because I'm going from a hot to a cold, or to a lower temperature, right? A higher temperature to a lower temperature. So here we go. Now we just substitute the numbers. You get 2.34 number of moles, gas constant. And now just be careful here. TC is 549. Minus 720 Kelvin. We have that change in internal energy for that process BC gave me a value of minus 4,980. 4,000, and that is measured in joules. Now, if you think about the next one is going from D to A. Well, D to A, it's going to be a similar calculation. Right? We still use the same equation. So the change in internal energy for that case, again, 3/2 NR. Now, what is the T final minus T initial, or my delta T value? My T final now is the temperature at point A, and my T initial here was the temperature at point D. So I get the exact same numbers, except these are going to be reversed, right? It's going to be 720 minus 549. So at the end here, you're going to get positive 4,980 joules. Let's go ahead and fill this out in our table. So here in minus 4,980, here I get positive 4,980. All right. And now, well, it's very easy to find the work, right? The work is the exact same value as the change in temperature for both of those. All right, so you just simply go back here and you fill this out. Minus 4,980 and positive 4,980. All right, now I also wanted to fill out the table by calculating what is the total heat for this entire process if I go around this cycle. All you have to do here is sum all of these quantities, right? And then just fill out this last row of values. So let's go ahead and do that. All right, so if you sum all these values here, what you get is 1,560 joules, okay, for this total heat over the cycle. The work done on the gas then has to be minus that value. You can see those are going to cancel out. You're going to be left with the same numbers, just with a negative sign in the front. So minus 1,560. And if I start at A and I go all the way back to A, clearly there can't be any change in internal energy over there. So this here always has to be 0 if I do a cyclic process. Okay, so there's no change in internal energy of that gas. All right, the last thing I want to calculate here is the efficiency. The efficiency for any cycle would be the work done again, by the gas here. So be a little bit careful. The work done by the gas divided by how much heat did you actually put into the system. So let's go ahead and think about this. The work done by the gas is going to be related to this value, right? This was the work done on the gas. So guess what? The work done by the gas would simply be minus this value. Okay, so it would be 1560, and it simply represents this area under the curve here, or the area within this cycle. Now, how much heat did you put in? Again, there is heat going into the system over here, and there is heat going out of the system here. So during this isothermal expansion, the amount of heat that goes into the system was 6580. Okay, you put those numbers in your calculator, and you should get something like 0.237. This is equivalent to 23.7% would be the efficiency of this cycle. Now, for the Carnot cycle, if you did a little bit of math, you could show by substituting in some equations here for the work done by the gas, some of the previous equations I presented, and also for the heat in. If you actually substitute the equations in, you can show that the efficiency of the Carnot cycle is given by this expression. It reduces to this. I'll just write it like this. TC is the cold temperature. So this isothermal compression over here happens at 549, and TH represents this hot temperature, okay, for this isothermal expansion. Again, if you substitute the values here of 549 over 720, you're going to get to the same value over here, okay, for the efficiency of the Carnot cycle. This equation, the first one, works for any cycle, okay. You simply need to calculate the work divided by the amount of heat that gets put into the system. This last one over here, this is specific to the Carnot cycle. Okay, it's because the algebra just works out that if you substitute everything in, it reduces to this simpler looking expression. All right, folks, thanks for watching. That's it for me.